My name is Thabo Ngwenya. I'll be presenting my predict for is to model the shortfall between the energy generated by means of fossil fuels and various renewable sources. So the daily shortfall as a target predictor variable is to be used to gather insight with all the combination of features such as pressure, wind, speed, humidity, rain. So meeting the electricity demand through various electricity resources against daily weather conditions. So we'll be predicting on a daily how much energy was used, how much energy is possibly needed, and uh, and how much demand on each of these renewable resources or non-renewable resources is needed for future. So I think we'll cover that on the next slides. So how weather influence or affect energy consumption on a daily basis. So that being rain, cloudy, stormy, cold front, hot wind, humidity, foggy, as well as not forgetting just to add there the time. So that will be season, month, day, hours. So morning, noon, evening. So how we factor those in. So depending on the season, right? So winters are known to be rainy, are known to be cloudy, are known to be very cold front. So meaning that if we were to look at the solar solution, it will be very difficult to produce energy via solar since it will be cloudy most of the time. So that will affect that resource, and that will put a very much strain if, let's say, the country of Spain um, uh, had a dependency on had a 30% dependency on solar. That means on these seasons, winter seasons, they won't be able to generate as much energy from solar. Here, we're just talking about renewable and non-renewable sources. As you can see there on the graph there, and graph we have like hydro, nuclear, wind, solar, bioenergy, and then other non-renewable. So here I was just showing non-renewable sources. Uh, so which one is on demand, which one is used, favorables, and all those things. So if you look at the right, effect of weather to energy that needs to be generated via season. So as I've mentioned on the previous slide, so here it's covered much deeper. So strong winds equals to windmill. So if you creating energy through windmill, that means on that season where you experience strong winds, you'll be able to generate more energy. Where there's a season where it's clear skies, meaning that you can generate more electricity through solar, as well as hydro through rain and stuff. So meaning that you'd have a lot of water. Relation heat map to assess the relationship between all variables in the data set. So here we were checking the relationship that all these variables would have to one another, and also the load shortfall. So there's some scales there. If you look at the diagram, the top diagram, you can see on the sides the scales from -1 to +1. So this scale simply means that the closest to one or one, that means have the very close relationship. But maybe let's say -5 or so, that means the relationship is not as close, and it's far off having a relationship there, comparing these variables. As you can see on your y-axis and your x-axis, you can see the relationships there when you check. Also, maybe if you interpret it as a 2D array, you can check there to say column 3, row 4. As you can see, column 3, row 4, maybe you can say Madrid pressure and Bilbao pressure. You can see, okay, the relationship there is 0 0.43. So there's no relationship there, or there's no strong correlation. The correlation is said to be weak if we're using the right terms. And using ketosis to assess if there's any outliers in the data set. So using ketosis, so it's a function or functionality in statistics where we check if the data or data set that is provided, we can refer to, as you can see on the diagram, the first one on the left, we can refer to it as maybe Bilbao rain. That will be a variable that would influence our prediction that's needed. So as you can see there, 32, meaning that there's a high number of outliers there. So the closest to one, um, the closest to one, or the closest to zero, meaning that there's less outliers, and closest to one, meaning that there's somewhat some outliers, but 32, meaning that there's a high number of outliers there. So it's out of the range there. So using skew to measure the symmetry of each variable. So skew, how we can better also show it is when maybe we can plot it, but so if it's closest to zero, it means that it's almost like a flat line. It goes up and then just bounces straight down. So, but if it's like your one, meaning that it's a perfect symmetry. How we calculate according to uh, to the numbers. Yeah. So checking data types of each variables. So these are the steps and procedures that you take to check your data of any anomalies, outliers. If you do need to be doing something, so already before you get to cleaning your data, you can, these processes are used to check if your data is clean enough, compatible, and all the stuff. So you can checking for nulls, and checking the data type objects, if a particular, if maybe the data is of an object type that will which enable you to process it much simpler, sort of like maybe dealing with integers and floats. So yeah, so going to the next slide, adding new features from existing data sets. So as you can see there, once the data is analyzed, you can break down the data. When you have understood the problem, so as you can see there, number one, for instance, time on your left, you can see the column, there's time there. So we've broken down even further, created smaller features, uh, created year, and then created variable month, day, and hour. So yeah, we can use as a global scale, to just say, all right, a year, for this year, we had so much energy consumption. And then month, we can use, say, okay, for this month, we had so much. And then month can also influence the seasons. So we can say, okay, we have this season and other season quarterly. So maybe we have like 4 seasons. So meaning like in a year, we have 12 months, and then you divide that by 4, and then you can just get these, you can get these uh, three, three, uh, three, 3 months of each season. So winter, the other 3 months, so forth, so forth. And then we can have a day where we check the overall changes for the day. So the weather can change like 3 times or more times in just one day, as we have seen in some other seasons. And then we can have 3 hour 3 hour intervals. We can have hours, where we can have 3 hour intervals where we assess the changes for the day. And then we have like categorical data there, as you can see on the screenshot, where it's categorized by levels. We can break that down and create other smaller features or dummy data. Say, okay, level 1 is 5%, level 2 is 10%, and so forth. So that's feature engineering. So our hypothesis. Um, The energy demand on the resources is going to be high in the future, judging from the model performance and the graphical representation. The demand on renewable energy resources will fall short as other factors contribute to electricity load shortfall. Um, so various variables that may affect the outcome, like global warming. Maybe if you can put global warming scale percentage a year, how much the country of how much does the country also contribute to global warming a year with these non-renewable sources, maybe the coal that is burning, how much are we contributing, and the population, how much are we burning, and then how many trees have they planted, then population increase. Then the second point, population increase or decrease. The more the growth, the more demand on resources. So as we have seen, the more population, the more demand on the resources. And then time, peak hours can show more demand than off peak. So time, maybe early in the morning, people are preparing for work, the geysers are on, everything, people are cooking, and also maybe late in the afternoon, then the electricity demand is quite low because people are at work, people aren't home or cooking and doing all this hectic stuff. And then other factors is season. So factoring by season, as on the previous slide, as I've highlighted, how season can influence our prediction. If winter, we have higher electricity demand and all the stuff. But we can already work out that from the data set that we got, since we have these weather um, uh, 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 weather variables, where we can just get, okay, since we're experiencing so much coldness around this time of the year, and create a new feature and say, okay, this is winter, experience more rain, this is spring, and so forth. So once all the stuff is done, the data engineering is done, then we can feed this data and create a new separate features, and then we can feed this data into models, where now I've created linear model, linear regression, decision tree, and random forest. So I've created the tree to get the highest prediction or probability, um, using 3 different techniques or 3 different models. As you can see, the one that came with the lowest RMSE score was random forest. As you can see as well from the far right, you can see how the linear line is fitted nicely compared to the other ones. As you can see there, the consistency. So that's it from here. And then in conclusion, we should be thinking about different variables that can influence the load shortfall in energy demand. The more the data we have, the better our model will perform and give us close enough prediction results. Predicting the future through time series needs a lot of variables that influence the decision or the outcome. I